Welcome to our video.
Emily. Hi.
Hi.
I decided to make some hot chocolate while I waited for everybody to get online.
Oh, okay.
So I'm gonna go finish making my hot chocolate, and when everybody gets on, you can tell them that, you know, that's why there's no one in the window.
Okay. All right.
All right. still just you?
Yeah.
All right. All right. So I got my ladies. Emily Carr, are you going to turn on your microphone and your camera? Thing 2. Paging thing 2. All right. Well, Emily, were you able to do your reading and watch your videos before today?
No.
What? No?
No.
Okay. Did you take your test?
Yes, I did.
Okay. When did you end up taking your test? I know that this weekend was really hard.
Just today.
Yesterday? Okay.
Yeah, today.
All right. So you're going to have 4 videos to watch this before the end of this week. So.
Oh, wait. 13? The video is for 13?
14.
Oh, yes. I watched the first 2. I thought you were talking about the ones that you just posted to Edmodo. Just due for Thursday.
Confused. What?
Let me see. I watched 14.1 and 14.2.
Perfect. Yeah, that's what I was asking. If you watch those.
Oh, okay.
All right. So here's the thing. I'm pretty sure that Jordan is not going to be joining us because his mom never answered her phone. So let's go ahead. What is the deal? Is somebody's computer messed up?
I think it's Emily's.
All right. Testing. Testing. Emily, do you hear it that weird way too? Okay. So I'm gonna have to mute her.
I think you muted yourself.
Oh, so that was just muting me.
You're muted too, because I can hear you.
Let's just see if this helps. Oh, good. She did. All right, it's good. That works. So, Emily, you'll just have to type in all of your answers. Got it? Sorry about that. All right. So we're starting with types of mixtures. And we're going to do this really quickly because this part, I think, just is really self-explanatory. 14.1 was not a hard chapter. I will say this. There are a lot of terms on this this chapter's quiz and this chapter's test. There's going to be a lot of terms and a lot of math. It's a heavy both side, heavy in both this chapter. Hang on, Joel's awake, so I got to go get him. Joel's awake. I know. I know. Yeah, that really hurt when I looked. So I tried to kiss Joel's head and I bit my lip. It really hurt.
Yeah, Wow, that sounds terrible.
But all right, so let's get started. By the way, his poor little arm. Look, see what he did to himself?
Oh no.
Yeah.
Is it a blister?
Yeah. Well, it's part of it is a blister, part of it is just scraped up skin. Say hi. I know. You'll see Dada. He reached his hand under the vacuum when his Meemaw was vacuuming.
Oh my word.
He tried to grab some popcorn. Yeah. See, that wasn't a good idea. Oh. All right. Yeah, go see Dada. He'll give you a drink. Oh, well, now I got a clingy baby. Anyways, 14.1 is pretty self-explanatory, but I do want to go over a few main points. I did actually get the hot chocolate so I could talk to you about something. So, no, what? He's going to hold this now. All right. So, starting with the difference between a suspension, a colloid, and a solution. We're going to start there, okay, guys?
Mm-hmm.
And Emily, you can still hear us even though you're on mute, right? Good. All right. What I'm going to do is screen share, and I've got a couple of videos that I chose. The one I didn't have time to view, so I'm hoping it's good. We may stop and skip that one, but we'll see. I know I watched the other one, so screen share and whoa, hang on. Start screen share. Let's go over to Safari. It's like a never-ending reason. All right, here we go. So this is the one I found first.
Suspensions, solutions, and colloids. With me, Will Nye, the science guy.
I guess he's got
First up is solution. A solution is a homogeneous mixture of two or more substances. It is always transparent and can pass through with no scattering solute particles. Here's an example of a solution.
This is why I chose this. I wanted to see an example.
Mixing sugar and water.
Don't. Come here.
For solution, light can easily pass through the... Wow, that's amazing, Sean. Alright, next up is suspension. A suspension is a mixture containing large dispersed solid particles that can settle out or be separated by filtration. An example of suspension be combining or mixing oil and water. For suspension, the particles easily separate and light can easily pass through. Alright, and the last one is colloid. A colloid is a mixture containing solid particles small enough to remain suspended and not settle out. An example of colloid would be mixing mayonnaise and water.
Ew.
Boogers?
For colloids, light is very hard to pass through. So you can't see the light. Alright, thanks. And this has been...
Alright. This one's better. I cut it to the video part that I wanted. This is a demo between showing you the Tyndall effect.
Glass bottles. One filled with water, and the other filled with water and some soap. We're also going to need a flashlight. As you can see, when light is shown through the bottle with water, you can't see the beam of light passing.
Moving to the bottle with the soap and water, you can see the beam of light passing through the bottle. This is what's known as the Tyndall effect, and it is caused by the reflection of light by very small particles in the medium. In this case, it's the soap particles in the water. Anyway guys, that's gonna be it for this video. If you learned something from this video, leave a thumbs up.
By the way, this guy was, I don't remember what his name is, but there's the way that you can find it. All right, guys, let's stop screen share now. All right. So,
Mom,
explain to me what you just saw.
is there a problem?
Hello.
Sorry.
All right. So what's the difference between a suspension, colloid, and a saturation? I'm sorry, not saturation. Wow, a solution.
What's the difference between suspension and solution?
All right, hang on. Ready? Da-da-da-da. Let's start more broad. I would suggest knowing the difference with the things that I'm going to take the time to point out with this chapter. Those would be very helpful. They're good essay type questions, and you're going to have a lot of essays on this test. So yeah, I want you to make sure you're taking careful notes as I point out the main categories where these differences matter.
Mm-hmm.
So first, broad category, homogeneous, heterogeneous mixture. What's the difference?
Homogeneous or homogeneous.
Yeah, you can say it either way.
It's even. It's mixed together. I don't know what that word is.
Completely mixed.
Completely mixed. Heterogeneous is when there's like a difference, like rocks and water. Those aren't together, mixed together.
Okay, good. So there's distinct parts. That's actually the difference you can even tell with homo and hetero. Mm-hmm. Homo means same. It looks the same throughout. Hetero means different. You can see distinct different pieces. I want you both to type an example of a homogeneous and a heterogeneous mixture right now.
Sorry, I didn't mean to press enter.
No, that's fine.
That'd be homogeneous. And then
good, because it's all mixed together.
Heterogeneous. Rocks and water.
All right, Emily Carr, where's yours? Salt water is good. That's good. So where could be a mixture with different pieces? Yeah, cereal. You got milk and you got your cereal. Good. I was going to say fruit salad or like fish in water. You have fish and then you have water. There's different pieces. So that's definitely heterogeneous. Now, inside of these categories, homogeneous can also be called a suspension or a solution. So that you should know. Solution. Homogeneous is also called solution. Now, heterogeneous. There's two types. Heterogeneous is going to have suspension. Colloid. Let me make sure I spelled that right. Colloid and the suspension. These two are different. All right, colloids and suspensions. So you want to make sure you know how to tell the difference between homogeneous and heterogeneous, and then how to tell the difference between colloids and suspensions. All right, and also that solution is another word for homogeneous mixture. So a colloid is very, very, very small pieces. Have you ever seen a ruler that's got the metric system on it?
Mm-mm.
All right, well, hang on. Let me see. Nope, I don't think I'm going to take the time. Anyways, on a ruler, next time you look at it, look at the millimeter side, or the meter side, right? And look for millimeters.
Oh, yeah.
And the millimeters, like you have centimeters is about the size of your thumb.
Mm-hmm.
And a millimeter is like when you cut that, let's say milli, you're going to cut it 10 more times. So it's really, really small. Well, if you take a millimeter and you cut it into 1,000 pieces, and then you take one of those pieces and cut it into 1,000 pieces, that's how small we're talking about when we talk about colloid particles. So they're really, really small. And because they're so small, just the movement of water collides with the pieces and actually elevates them and keeps them, hi baby, keeps them floating. So that's why they exhibit things like the Brownian motion and the Tyndall effect. Hi baby. Mwah. Mommy loves you. Mwah. Careful, where's your ball? Go show me your ball. All right, so the difference with a solution is solutions settle out if left undisturbed. Just like you said, the rock. Oh my word! Hey, Bubba, you climbed up. Hang on.
Band-Aid.
Do you want me to go into the bedroom? Well, if you stay in the living room and play with them, I'll be better with the sound for me to go into the bedroom. So you tell me, are you going to play in here? That'll be fine.
Come on, Bubba.
All right.
Ready?
Thank you. Hey guys, I'm back.
Okay.
All right. I think we were on suspensions. They will settle out and left undisturbed. So look, if you take water and you put sand in it, what's going to happen if you mix it up so that the sand is all elevated or the clay is all elevated? What's going to happen over time?
It's going to level itself out.
It's going to settle out to the bottom so that all the sand and the clay is on the bottom of the jar. All right, so that is a suspension and not a colloid, and you need to know the difference between them. Now, the other thing about this, like what we saw in there, is that the Tyndall effect will only happen to colloids and not with your suspensions, all right, or with your pure solutions. So Tyndall effect is where the light is scattered as it goes through because it's hitting the particles, all right? So as it hits and collides with other particles, it's being reflected out. Like when you see color, for instance, what color is this iPad?
Blue, purple.
It's purple, yeah. It's kind of bluish on this because it's weird through the camera, but it is purple. So what's happening to make this look purple? When your eye sees purple, what's happening to the light?
Reflecting off it?
Yeah, the light goes from the window or the from the light bulb, and it goes and it travels. And remember, white light has how many colors in it? Or which colors does white light have in it? Emily, type it in too.
A lot. I don't remember how many.
White light is composed of all of the colors. That is right. Roy G. Biv. It's got every single one of them. When it hits an object, what happens is the object will absorb some of the colors and reflect some of the colors. For you to see purple, which colors are being reflected?
Purple?
The purple. You wouldn't see purple otherwise. So this is actually everything but purple because it's absorbing all those colors, but it's reflecting purple, and that's what our eyeball sees, and then we go, that's purple, because it's the only color that's reflected, which is why we can get so many shades, because some objects absorb so many different things and reflect many different, which is why you can have so many shades of blue and all the other things. So anyways, think of that when we're thinking of the Tyndall effect. In order to be seen, the light has to be reflected. If the light is traveling in a straight line, it's just going to go straight through, and it doesn't really shine. We don't see it until it's colliding with something that it'll reflect off. And that's when we see the light. So as it goes through the bottle, if it collides with just water, it's just going to keep going through, and it's not going to get disrupted. But when it collides with something that's floating through the water, like the mayonnaise, it's going to hit the mayonnaise and reflect off and actually be visible to the eye because of that. So that was the Tyndall effect. So we've gone over homogeneous and heterogeneous mixtures and the Tyndall effect. We also need to go over Brownian motion. This is actually discovered by our scientist who was Robert Brown, and he was actually a botanist. He studied flowers and plants. He came in one day with from working in the fields, and he had some pollen get from his coat into the water he was about to drink, and he watched it. And instead of throwing it out and getting new water, because you know that's what normal people do, he sat and he watched the pollen, and the pollen moved around weirdly in the container, and it never went on a straight path. It was like a random jerky kind of motion. And so he actually got to thinking about what caused that, and that's what caused the explanation with Brownian motion. And what Brownian motion is described as is the erratic, jerky motion of the particles that are in solution or suspension, and it's caused by the collisions with the water molecules. So I want you guys to think of if I took and got everybody from your youth group together, and I put them in a small area, and I blew up a beach ball. And I threw the beach ball into the, the big beach balls. I threw the beach ball in, and everybody like started hitting the beach ball. Could you predict where the beach ball would go? What would the motion look like?
Just be a bunch of zigzags and crazy lines.
Good. What would make it zig one way and then the other?
The fact that people are pushing it.
The fact that people are pushing it. And if more people push it on one side than the other side, it's going to go that direction, right? That's Brownian motion. At least that's an example of Brownian motion. It's just that's happening with water molecules and the pollen or whatever is in the water. Make sense? All right, look, I'm going to go ahead and say that's a wrap on 14.1 and go on. You guys do have to take the time to study the concepts here. Remember, this is a big essay section of your test, so make sure you're knowing the differences. Got it?
Okay.
Now I want to spend more time on the math, because I understand it's harder to study math when you're at home, right? So we're going to go on to 14.2, which introduces concentration. And that's why I got my tea, or my hot chocolate. Look, this is pure water right now. So see, just clear, right? And what I'm going to do is take and make some hot chocolate. So I've got my mix, and what am I going to do with this?
Pour it in the water.
I'm going to pour it in the water, and then I'm going to do what?
Stir it up.
Stir it up. What if I only pour half of the mix in there?
It'll be not as good.
All right, so it's going to be kind of watery still, right? Not very full of hot chocolate, right? What if I pour more of this, like all of it? Compare the two. How would you compare the two? One is more what?
Concentrated.
One is more concentrated. That's what we're talking about today. We're talking about concentration. And in order to be more concentrated, what did it have to have more of?
The powder.
More of the hot chocolate, right? The thing that was dissolved, you had to have more of it. Make sense? What would you call something that doesn't have as much? Like when I started and I only poured in one packet of hot chocolate, or like half the packet. Look for a word. They actually give you a word that's opposite of concentrated. It's on page 480. The opposite of concentrated could be described as being...
Do they have it in here?
Starts with a D. It's not bold. You have to actually look for it. Diluted! Yay! You got it. It is dilute. So the opposite of concentrated is dilute. You can actually describe the solution as being dilute if it doesn't have as much stuff dissolved in it, and concentrated if it has more stuff dissolved in it. In this case, the stuff is the hot chocolate. Now we have some terms we have to know. You must memorize these terms. The difference between your solvent, your solute, and your solution. These three terms are going to be referred to in all of these equations. You have to know the terms in order to use the equations. So it will do you no good to memorize these equations and not know which thing it is. So let's define them. The solvent, V, right? Solvent. That is the thing that is very big. It's always the most plentiful thing. It's the one that's doing the dissolving. The solute is the thing that's being dissolved. It's smaller. So in this situation, my hot chocolate, what was my solvent?
Your solvent was the water,
The water. What was the solute?
the hot chocolate.
The hot chocolate. And then the solution is everything together. The solution is my lovely, yummy hot chocolate drink that I would drink, you know. It's both together, right? So that is the difference between those three terms, and you have to know them because we're going to be using them with these equations. Now, I want you to memorize the equations on 14.3. Do you see this table? Even though it seems like there's a lot of them, there's really, if you combine them, there's not as many as this seems. Percent by mass and percent by volume are pretty much the exact same thing, only one is focusing on mass and the other is volume. So those, if you memorize that and you just think in your head, oh, these are interchangeable, it's the same equation, okay? Molarity and molality are so similar. It's the only difference is that one is the liters of solution on bottom, the other is kilograms of solvent. So that's pretty easy too. And then we'll have our mole fraction. We'll talk about that later because it's different. So it'll be the one that's weird. We also will add, write it down because it's one that's not in this table. We're going to have a dilution equation as well. I forgot that your quiz, I think your quiz covers section 14.3 as well, so you'll have to wait to take the quiz until after our lesson on Thursday.
Okay.
And then our test isn't going to be until next week because next week we have a lab day on Tuesday and then a review day on Thursday, and then you'll take your test. So you'll be working on this material for 2 weeks.
Okay.
And then you'll take your test. All right, so add this equation to it. M1 times V1 equals M2 times V2. That's our dilution equation, and we're going to be talking about that later, but that's the one that you don't have here and you have to memorize it. Okay, so that's the dilution equation. All right, now let's just practice. These really are simple. Have them in front of you for today, but work on memorizing them from here on out, okay? All right, so let's look at the first example on page 481. Essentially what we're going to do, guys, is we're going to go straight through these problems. We're going to do all, hopefully all of them. We're going to do as many as we can in the half an hour that we have left, okay? So we're going to try to get through as many of these as we are able to. Let me do this. I'm going to start by doing the first for each one, and then you guys might have some homework with these afterwards, but we'll at least have done one together like on the video, and you might have to finish some for homework.
Okay.
So let's start with number 9. What is the percent by mass of NaHCO3 in the solution containing 20 grams of NaHCO3 dissolved in 600 milliliters of H2O? So help me out, guys. Let's start by talking about this problem. What do you need to solve this problem? What's the equation for percent by mass?
I don't remember. I'm going to get my calculator real quick. Actually, it's right here.
Look on page 480. What's percent by mass? Good. Grams, and then the solute and the solution. That's it. We need the mass, so that's grams, and we need the solute and then the entire solution on the bottom. Now look, the funny thing about water is that its density is equal to grams per milliliter, and it actually works out that 1 gram of pure water is equal to 1 milliliter of pure water. So whenever they give you this problem, if they give you milliliters of water, that is equal to the grams of water. It only works for water, though, because of the density of water, and so we will be able to turn milliliters into grams. Now, I want you to tell me what's going to be in the numerator on this problem.
The mass of the solute, which would be
Which thing is being dissolved?
the bleach solution.
Good, the NaHCO3. So we're going to have 20 on top, divided by what on the bottom?
Oh wait. We're on
What's the solution? The solution is what?
Sorry, I was on problem 10. So, I'm confused.
The solution is supposed to be everything. Did they give you the mass of everything yet?
No.
No, so you actually have to take 20 plus 100, or sorry, 600.
Mm-hmm.
So your problem should look like this. It should be 20 over 20 plus 600, or 620. See? When you push equals, that's the first thing. But then we have to do what? Because it's a percent.
Divide, multiply.
Multiply by
100.
Multiply by 100. Notice that that's why it's here in the equation. It says mass of solute over mass of solution times 100. So we take this, multiply by 100, and what do we end up with?
3225806.
Good. So how many significant figures am I able to write?
3.
3. So I'm going to write this as 3.23%. Make sense?
Mm-hmm.
Any questions?
Yeah.
All right, guys, let's go ahead and let's go on to the next one really quick. You can do the other one when we're done here. Let's start with number 13. This one says, what is the percent by volume of ethanol in a solution that contains 35 milliliters of ethanol dissolved in 155 milliliters of water? Now in this one, it is percent by volume. And look, you can use milliliters or liters or deciliters or centiliters. It doesn't matter as long as both units are the same. If both units are not the same, if they give you liters and centiliters or liters and milliliters, you have to convert one of them. It doesn't matter which one you convert, but make sure they're the same, and then you can do this problem.
Mm-hmm.
So check first. Are these units the same?
Yeah. Both milliliter.
Both are milliliters. Good. So now we can use our equation like it's normal. So what's going to go on the top of the fraction?
35 milliliters.
What?
35 milliliters.
35 milliliters. Good, because that's our thing that was dissolved, the ethanol. Over everything. Remember, over the solution. So what is that?
155.
It's not just 155.
190 then for adding everything?
Yes, we have to add them. Because look, if you put the solution over the salt, just see that. If you had just put the 155, that would have been over water. That would have literally been the solute over the solvent. That would have only been the solute over the solvent. See? But you needed the solute over the solution, which is why we had to add 35 plus 155. Because that's everything on the bottom. I will agree with you, Emily, except for your sig figs. So just only how many sig figs? 2. So we're going to round that to what? 18%. Yes. Don't forget to include your percent sign because these are percents, and that's going to help with the making sure your answer is completely correct. Okay? All right. So now we're going to go on to, look, see, are these easy?
Yeah, they're easy.
They're pretty easy, but you have to know the equation. But those two are exactly the same type of problem, aren't they?
Yeah.
So now we're going to go ahead and go on to number 16. And with number 16, remember, this is going to be asking for molarity. And molarity is a unit of measure to figure out moles of solute over liters of solution. So moles of what's being dissolved over liters of everything. Those units are important. We need moles, we need liters. So let's read the first problem. What is the molarity of an aqueous solution containing 40 grams of glucose in 1.5 liters of solution? So did they give us moles and liters?
They just gave, grams and liters.
They gave us grams. So what do we have to do with our grams before we can use this equation?
Turn it to moles.
Convert grams to moles. Good. So you're going to take 40 grams and you're going to divide it by the molar mass of glucose, which, by the way, I'm going to save us some time. This is the molar mass of C6H12O6, 180.16 grams per mole. That's my molar mass.
Mm-hmm.
So how many moles does that give you?
I don't know. Do we have to do something first? You said 40 grams over 100.
Yeah, you're going to do 40 divided by 180.16.
0.2220.
Yes. So take that number, and then that's my moles of glucose, which is my moles of my solute. And I have to put it over my what?
Over or under?
Look at your equation and you tell me.
That goes over.
Yep, look. 0.222 moles divided by the liters of your solution, which they gave us liters of solution, so we don't even have to convert that one. So it's just divided by your 1.5. And what's your final answer going to be?
0.148.
Yes. What's your unit?
Liters?
Nope. Look, if you have moles over liters, they're not going to cancel. You could write this unit as a capital M, which means molarity, or you could write it as moles over liters. Either one, those two units are the same thing. Molarity is moles over liters. I really need to stress to you the fact that capital M, molarity, is different than little m, molality, and we're going to be talking about those two today in a second. So you need to know the difference between a big M and a little m.
Okay.
Do you guys want to do another one here, or you feel like you can go on?
One more.
I'm sorry, I didn't hear you.
Yeah, one more.
One more? Okay, go ahead and you guys do number 17, and I'm just going to listen to you talk through it.
Okay.
Or in Emily Carr's case, type it out. I'm going to watch her type it out.
Okay, so we need to do 155. Number 17. Number 17.
Number 17, yeah.
Okay. So 155 grams over the molar mass of KBr.
Okay, good. But that's 1.55, not 155, just so you know.
Okay. Okay.
Yep. Okay. So Emily, then take your next step when you get your moles with that, and you're going to divide it by what?
So I have 1.55 divided by the molar mass, which is 119.
Yes. So 1.55 divided by 119. Emily, notice, look at your liters of solution. Do you already have liters of solution? In the problem, did they give you liters of solution?
Are you talking to me?
No, I'm talking to the other one. Sorry. Yes. So you don't have to do the plus 0.013. You don't have to add anything to the bottom. You're going to just take your 0.013, which is your moles, of KBr, and you're going to divide that by the liters of the solution, which is 1.6. See? So you don't have to do anything. I don't know why you had the plus. It's just it's divided. Does that make more sense, Emily?
All right, my answer is 8.13.
Is that it, guys? Just 8.13. Let me check, because I think that mine tells me I need an exponent. Let's see, 0.013 divided by 1.6. Yeah, look, because you have 0.008125 or 2.
So the exponent would be 10 to the negative 3.
Yeah, you can do 8.13 times 10 to the negative 3. That's fine. That is our final answer. Emily, you're not doing a percent, so yep, so not a percent. And so did you multiply or something? Is that where you got, Emily, did you multiply by 100? Because that would give you 0.81. You don't need to multiply by 100. Like, you only multiply by 100 when you're doing percent, and those are the percent by volume and the percent by mass. This is just molarity. There will be no multiplying by 100 on this. So it was just 0.00813. And you can put that into scientific notation by shifting your decimal, or you could leave it like that. Good? Okay. All right, guys, turn the page. This is where we got to our dilution equation. Oh, never mind. We're doing one more before. They're going to ask you to go backwards with this, with molarity. You're going to be working to use molarity to find mass. So notice the first question, number 20. How many grams of CaCl2, so look, we're looking for mass in the end, would be dissolved in 1 liter of a 0.1 molar solution of CaCl2? So let's talk through this, guys. Look, molarity is what? What does molarity equal? Write it down for me. What's the unit? Big M equals what over what? We just got to
Moles over liter.
moles over liters. That's important. See how big M is moles over liter, right?
Mm-hmm.
So when they give us molarity, we can set this up as a stoichiometry problem, or we could just multiply and divide to get to what we want, right? So let's look. They gave us 0.1 molarity, right? 0.10 capital M. I'm going to rewrite that unit as moles per liter. right? So I have 0.10 or 0.10 moles over liter. Now, I want to see, I have 1 liter, so I have to multiply that. Oops, I'm doing this backwards. I'm sorry, hang on. Let me just write it out. It's too hard to think of it, how to do it without writing it. Paper, I need a pen. I'll be right back.
No. No.
Okay, I've got a pen now. All right, sorry about that. So start with the volume that they give you, and we're going to use molarity as a conversion factor after all. So we're going to take our point, what was it? Our volume was 1.0, 1.0 liters. Ta-da. Now, we're going to use molarity. Molarity, if I have 0.1 molarity, this is equal to 0.1 moles over how many liters?
2.4. I don't know.
Remember when we're doing a per, it's the same thing as moles per liter. This is the same thing as like miles per hour. If you're going 65 miles per hour, you're going 65 miles over 1 hour. So 0.1 molarity equals 0.1 moles over 1 liter. See how you can take the molarity and split it up so now it's a conversion factor? So look, up here, think of it like any other stoichiometry problem. What has to go down here to cancel?
Liters.
Liters. So we're going to put our 1 liter on the bottom and our 0.1 moles on the top. What will cancel then?
The liters will both cancel and we'll be left with moles.
The liters will both cancel and we're going to be left with moles. So take 1 and times it by 0.1. See what you get.
One point zero. I'm not working for some reason.
You said what? 1.0. Okay, good. So it's just 0.1. Yep. Or 0.10. See? But now it's just moles because we canceled our liters. See? Now this is moles of which thing? Which thing was the thing that was dissolved? So which one is the solute? Read the problem. How many grams of CaCl2 are dissolved in what?
CaCl2.
Good. CaCl2. So now we have moles of CaCl2. How do you convert moles of CaCl2 into grams?
Conversion factor. Gotta find the molar mass.
We do stoichiometry. What goes on the bottom?
Grams. No, 1 mole, and then
1 mole, so it'll cancel.
and then the molar mass of CaCl2 on the top.
And then the molar mass of CaCl2 on top, like that. And then we're going to multiply, and we'll have our answer. So go ahead and calculate the molar mass of CaCl2. And then multiply, and you'll have your answer.
Where's
What, Emily?
Never mind. It's not it. It's 110.98.
Good. 110 point what?
98.
90?
98.
All right. 98?
Yes.
All right, so multiply that by 0.1.
Equals 11.098.
Good. And then how many sig figs do we get to have?
Just 2.
Just 2. So this is 11 grams of CaCl2.
Okay.
All right, guys, look, this is a just two-step process, and you could combine these two stoichiometry conversions so that you only have one line. That's fine, too. Go ahead and do number 21. How many grams of CaCl2 should be dissolved in 500 milliliters of water to make a 0.2 molar solution of CaCl2? So the nice thing is we already found our molar mass of CaCl2. So go ahead and start with your milliliters. And look, can you use milliliters when you're doing the molarity conversion?
With water. Is that what you're saying?
Can you use milliliters when you're converting with molarity, which is moles per liter?
Yes.
Not right away, you can't, because look at the first step. The first step was to convert our liters, or cancel our liters, right?
Mm-hmm.
So what do you have to do before you can use that number?
To turn into moles.
Before you can use 500 milliliters,
Mm-hmm.
what do you need to do with it?
I don't know.
What unit did you need here?
We needed to turn into moles.
Before you turned it into moles, what did you start with?
Liters.
Liters. You can't start with milliliters, you have to start with liters.
Mm-hmm.
So what do you do with your milliliters first?
Turn into liters.
Turn milliliters into liters, and then you can do the same steps with this problem. What are you going to do now that you have your 0.5 liters and you converted liters into moles? By the way, this is the 0.2 molarity. It's 0.2 moles over 1 liter. What do you do next?
Multiply and divide.
Yeah, you can multiply and divide. And you could get your number of moles. And then what would you do once you have your number of moles?
Are we going to find the mole? I don't know. The mass.
Change moles into
Liters, grams, something.
what are they asking for?
Grams.
Change moles to grams afterwards. All right. See, I'm just going to show you how it looks when it's all together. See how I don't have to do it as a separate step? I can also just attach 1 mole to grams right here.
Mm-hmm.
So I didn't have to do it as a separate step like I did up here.
Okay.
What's your final answer, guys?
Is it the same?
Yep, they tricked you.
11 grams?
This is the same problem, yeah. It's 11 grams.
That's annoying. Maybe they did find another number.
They tricked you. All right, so going on now, let's look at our molarity, our dilution equation. So what this means is molarity 1 times volume 1 equals molarity 2 times volume 2. What does this look like from chapter 13?
The P1 over T1.
Yep, that's it. It's our Boyle's law, specifically pressure times volume equals pressure times volume. Pressure 1, volume 2.
Mm-hmm.
Anyways, this is just like that. So the math is actually exactly the same. They're going to give you a molarity and a volume, and maybe give you a second volume and ask you for the molarity, or they'll give you a molarity and a volume and another, what did I say the first time? Volume? So they'll give you a second molarity. Anyways, you're just going to solve for one of the unknowns, but these are pretty straightforward. Let's go ahead and start on page 486, do number 24. What is the volume of a 3.00 molar Ki stock solution? What volume of a 3 molar stock solution would you use to make a 0.3 liter of a 1.25 molar Ki solution? So plug in my values for me. By the way, when doing these, you do have to have liters. So if you're starting with milliliters, convert those into liters for me before you start. Actually, never mind. You don't have to have milliliters, as long as they're the same. If you have two volumes, they have to be the same. That's all. So if they're both milliliters, that'd be fine.
Okay. So
first off, what am I looking for? Which one of these variables am I solving for? Am I solving for M1, V1, M2, or V2?
you are, I don't know, what volume? You're looking for volume?
I am looking for volume. Which one of my volumes? V1 or V2?
V2, I'm assuming.
Nope, this is the stock solution. Stock solution means the first one. So we're looking for V1. That's my X. What's the M1?
The M1, would that be 3.00?
Yep, 3.00 capital M. All right, what's my M2?
That would be 1.25.
1.25 capital M. What's my V2?
0.300.
Good. All right, so see, it's all set up. You just have to multiply this side and then divide by 3.00.
Okay.
All right, so I've got it.
0.125.
0.125, yep. And then there's 3 sig figs, so that would be fine. And this is which unit?
We're looking for volume, so that would be liters.
Look at what volume you used as the other volume.
For the other one?
Yes, liters, not milliliters. Good. Because look, this volume 0.3, that's in liters, right? If this is in liters, think about it. The molarities are going to cancel, but the liters is going to stay.
Did I say milliliters? I meant liters.
Oh, yeah, you said milliliters. That's why I was confused.
Yeah.
That's okay. All right, so dilution equations should be pretty easy. I'm not going to spend much time on them, okay?
Okay.
We're going to go ahead and go on to molality. Molality, moles of solute, just like the other one, but this is different because it wants kilograms, not grams. It must be kilograms, and it's got to be solvent, which is the thing that's doing the dissolving. So notice this is a symbol with a little m, and it means moles per kilogram. All right, so now let's look at the first problem. What is the molality of a solution containing 10 grams of Na2SO4 dissolved in 1,000 grams of water? So first off, what do you need to change to do this problem?
Put the grams into kilograms.
Grams into kilograms of water. Good. So you have to change the 1,000 grams of water into kilograms of water by shifting your decimal. So how many kilograms is that really?
Let me write out this real quick. So we're at gram, which is the base, and we need kilograms to be 3. That would be 33 spaces, right?
Mm-hmm. 3 spaces to the left. Yep.
So 0.0100.
You went to the right.
Yep, I did.
Wait, hang on. What did you say? Point what? This is really what?
0.0100.
Oh, you moved it 4 places.
I did?
Yeah, look, there's 1, 2, 3, 1,000. There's 3 zeros out to the left of the decimal.
Okay.
Hang on. You see this? 1,000?
Uh-huh.
1.
Oh, wait, I thought we were changing the 10.0 grams.
2, 3. No, because look, 10 grams is of the thing that's being dissolved. We'll have to convert that in a minute, but that's the second thing we're going to convert. I thought you were talking about the 1,000 because you said I think you said 1,000. You said grams, change grams to kilograms. When you said change grams to kilograms, that's only the thing you do for the solvent.
Okay.
Is water. So when you went kilograms, I went, okay, so change 1,000 to what? So now we know our kilograms. 1 kilogram. But we now need moles, right? Is this moles per kilogram?
A lot. So I have to convert 10.0 grams into moles.
That's it. Convert 10.0 grams into moles. I'm going to help you guys out because I want us to hurry this along. The molar mass of the Na2SO4 is 171.35 grams per mole. There you go. That's your molar mass.
Okay. And then 1 mole on top. That equals 0.5, 0.05836, etc.
Uh-oh. I gave you the wrong molar mass. Hang on. I gave you the molar mass for number 28. By the way, you could write that down. That's a molar mass for OH2. The molar mass for this is actually 142.04 grams per mole. I'm sorry. I'm sorry about that, guys.
It's okay. 4 grams per mole.
So I ended up with
0.0704.
yes. And then that's the right number of sig figs as well. So 0.704. Now what's your unit?
We have moles.
Moles per what?
I'm really crashing into this one.
What was your unit for water?
Grams of water.
Grams.
Moles. Grams per mole. Kilograms.
Kilograms. That's why we had to convert it. This is also a symbol of little m. You could write 0.0704 little m. That would have been just fine. Little m means moles per kilogram. It's what it means. It's actually really, really self-explanatory once you memorize these equations because it's right in the definition. It's moles per kilogram. So the unit is moles per kilogram. So it's like right there. All right, I'm going to have you turn the page. I would like to finish after this last example. Mole fraction. Mole fraction, I don't like the way that they show the example, so I'm just going to write the way that I like to write it out. Moles of over so in this case, what a mole fraction really is it's moles of what you want over moles of everything.
Mm-hmm.
Okay, so you're literally just putting Usually with this, you're going to have to convert grams into moles, and then you're going to just divide. It's usually a two-step process. If they happen to give you a fraction, like they do over here, the hydrochloric acid, they give you a percent, like a pie chart. Remember that we can assume that it's 100 mole sample, so we would treat that like our number of 100-gram sample, so we'd treat that like our number of grams. So if they give us that, we'd use 78 grams and then convert grams to moles, and then we use 22 grams. So if they give you a percent, just know that is your grams.
Okay.
All right, guys. Number 29. Tell me how to do it.
29.
What is the mole fraction of NaOH in an aqueous solution that contains 22.8% NaOH by mass? So remember, we have to figure out what's the rest of it. If it's 22.8% NaOH, how do you find out what the rest of it was? Let me draw you a picture, people. Where'd Emily go? There Emily is. All right, ready? I've got this lovely pie chart. This much.
What moles of what you want over?
This much is. This much is my NaOH, 22.8%. How much is this part?
Everything else.
That's everything else. So how do I figure out what the number is?
Subtract it by 100.
Yeah, take 100 minus 22.8.
We have 77.2.
Good. And that's aqueous. And so if it's aqueous, it's always water.
Mm-hmm.
It's always dissolved in water. So this is NaOH. And the other thing is water. See?
Mm-hmm.
All right. Now, mole fraction, really easy. Pretend that those are your grams, and you need moles. How do you get those grams into moles?
Convert.
Convert. So we're going to do 77.2 grams H2O. Convert that into moles, and then 22.8 grams of NaOH, and convert that into moles. I don't have the molar masses written down. You're going to have to look them up. I do know that water is 18.02. So you just have to look up NaOH.
Okay.
Jordan, I think I see that you joined the group, but your video is off and your sound is off. So go ahead and turn those on for me if you're able.
It's 40.
What?
40 for the molar mass for NaOH.
Can you tell me again what the molar mass of NaOH was?
40.
Oh, just 40?
I think, yes.
Okay. All right, so divide those. So I've got 4.28 moles of the H2O and 0.57 moles of the NaOH, right?
Yeah.
Now, mole fraction. Moles of what you want. Which one do they care about?
They care about the 22 grams of NaOH.
Good, they care about the NaOH. So look, which one of those was the moles of NaOH?
0.57.
So you put 0.57 divided by both of the other things, which is 0.57 and 4.28. So add those two together.
So we're going to divide 0.57 by itself and then divide 0.57 by 4.28.
What? No, no, no. It's what you want over everything. Look. So to find everything, you take the moles of this plus the moles of that. It equals 4.85, right?
Mhm.
That's the moles of everything. To find your mole fraction, it's moles of what you want, which is 0.57. That's moles of what we want, over moles of everything, 4.85.
Okay.
Make sense?
Yes. Zero 0.11752.
Good, but how many sig figs?
Just 3, so the 117.
The 7 rounds up because it's followed by a 5, so 0.118. And there's no percent. We don't have to multiply by 100 because it's not a percent, so we just write it as 0.118, and that's just said mole fraction. And Emily, how did you get 0.3? What did you do? Can I see your math? Will you type in what you divided by? Hi, Jordan. All right, so let's see. Emily, okay, got it. All right. Well, unfortunately for you, Jordan, we're about to leave. I tried. I called your mom twice. I'm sorry. I think her phone was off. Yeah, okay, got it. I'm sorry. I know that it was a different day and that it might have not worked well. Can you rewatch this video and just do the problems with us in the video? Okay. If you can't, Jordan, if you struggle, just give me a call and I'll help you with it, okay? But otherwise, I'm going to say, ladies, you did a good job. You do need to do some practice, though. So ready? Listen. We're going to do all of the practice problems, not counting the challenge problems. So don't worry about the challenge problems, but do all of the rest of the practice problems in this section 14.2. So I think we did, so that'll be number 10 and 11, number 14, number 18, number 22, number 25.
Okay.
And that's it.
All right.
So those are the homework problems for the written work. By Thursday, we are going to meet in person, and what we're going to do is just go over section 14.3 and 14.4, and we're going to turn in our test that you guys took and the quiz. Don't do the quiz yet. Thursday, you'll have to wait until after Thursday to do the quiz because it's covering section 3 as well. So wait on that quiz until after Thursday, and then you'll turn it in to me the week after. Okay?
Okay.
All right, so I'll see you guys tomorrow. And Jordan, hopefully this video makes sense to you, and we'll see you later.
All right. Thank you. Bye.
No problem.